Thank you. Okay. All right. Well, welcome everybody. This is our very first Amy virtual seminar series. We have a pleasure of having Jiadong Zang from University of New Hampshire kicking off our seminar series. We are very excited to be starting this seminar series that's open to anyone who's interested to follow along. Jiadong is a condensed matter theorist, who studies quantum materials and the theory of quantum materials. And he has made wonderful seminal contributions in the study of magnetic materials in particular. But I met Jiadong in the context of sort of this new adventure in the era of large language models, how we can now leverage the literature and the information that's scattered out there. So I met Jiadong at a conference, really impressive workshop that he organized, and that's where I learned about these latest results. We have in Amy, we are also very much interested in advancing how we do science with the new tools, and what we can build with more comprehensive understanding of the literature. So we have many of our members joining in today, logging in to follow along. So with that, stage is yours, Jiadong.
Okay, thank you, Una. Thank you for the introduction and thank you for having me. It's so honored to give the first Amy seminar today. So yeah, I'll share the screen. Can you see the screen?
Yep.
Okay, great. Yeah. So I'll talk about our recent efforts in building a database on magnetic materials, as well as other interesting compounds, and try to use this database to make predictions of new materials. So as Una said, my background is magnetism. I spent like 10 years working on the topological spin textures in chiromagnets. Then I found there were key materials issues in the broad context of magnetism. So magnetic materials has been used widely in the daily life, from the hard disk drive to wind turbine, electric vehicles. So they are so-called ferromagnets. And for these ferromagnets to function well, the magnetization as a function of the magnetic field should behave in this way. Right? So at large field, you polarize the magnetization, then you switch off the external magnetic field. The magnetization don't go back to zero, but remains a finite value called resonance. Then the magnetization will go away only when a finite magnetic field is applied in the opposite direction. And this is what we call the coercivity field. And this is MH curve, but you can plot the same thing in terms of magnetic induction. And the magnetic induction is following this red line. And the largest largest area of a square in the second quadrant give you the so-called magnetic energy product. And this is a key quantity showing the performance of a ferromagnet. So for example, the best ferromagnet so far is this neodymium iron boron. And you can see that the MH curve, MH curve is pretty square-like and form a very large area in the second quadrant. Okay? But this material was discovered like 40 years ago by accident. And there's no progress has ever been made after that. And this is a list of other native ferromagnets, but you can see that a lot of them containing rare earths. So there is a agenda in finding some alternative permanent without rare earths. So for example, so the rare earths, actually, they are not rare. And this is a a very interesting table showing the price of each element. Gold is very expensive. Platinum is very expensive. Once a time, I have a collaboration with a experimental group on the rhodium, and rhodium is even 2 or 3 times more expensive than gold. But rare earth elements, their price is decent, okay, but they are just vulnerable in the supply chains. Okay, so it's very interesting to find any rare earth free permanent magnets. Right. So these are so-called hard magnets, and the soft magnets are also very interesting. Right? So soft magnets has zero resonance and a zero coercivity field. And for example, they can be used in transformer or inductions. And for this, for example, the best material so far is the manganese zinc. Right? And they are working pretty well in the kilohertz region. But we want the inductors to work in a higher frequency region, and there is no good material candidate so far. And the magnetic materials can also be used for magnetic refrigeration, magnetic cooling. So basically, you apply magnetic field, and there is transition from paramagnetic state to the ferromagnetic state, and the magnet becomes ordered, and there is a change of the entropy, and this change is given to a system to make it cooling or heating. And the best magnetic cooling material so far is this gadolinium silicon germanium. Again, was discovered 30 years ago, and there's no other candidate so far, especially the rare earth free materials. So why the materials discovery is so difficult? So in the past, we know that the material discovery was entirely driven by experiment. But the new discovery of new materials is like Edisonian trial and error, not too much different from alchemy. But then there is a theory, there is the DFT calculations, but DFT calculations can mostly work on some small systems. But of course, recently we are seeing the capacity of DFT has increased a lot. Maybe there is some capacity of dealing with large systems. But strong correlations in some of the materials like magnetism and superconductivity still pose a challenge. So I would say that the understanding magnetic material to some extent is even more difficult than understanding the superconductivity. Because for magnetism to work, it's a multi-orbital system. Okay? So you do need not only the correlations, but also multi-orbitals. Right? So recently we have with the rise of the AI-driven or data-driven materials discoveries. So our goal is to see whether these new techniques can help us find new magnetic materials. And actually, there are some existing efforts in finding materials, magnetic materials driven by data. Okay, so yeah, you see, for example, in this work, there are some machine learning models that can predict the magnetic moment. And here, there's also prediction of the Q temperatures of the system. So by Q temperature, basically, it's the temperature under which the magnetization stays. But there are no big progress in literally identifying some new materials. The main problem is the data. Because for a data-driven material discovery to work, we do need a decent size of the data to train the model. Okay? But in the discipline of magnetism, a comprehensive database is largely missing. So this is a list of database related to materials. Okay? And they are classified into 2 categories. So one category is the computational result-based database. So they're constructed in terms of the DFT calculations. But on the other hand, there is also a list of experimental report-based database. So for example, in this category, materials project is the representative. It consists of a large number of compounds from DFT calculations. But they also claim that there is a class, some information of the mechanism. For example, the magnetizations and whether this material is ferromagnetic or antiferromagnetic. But due to the simple calculations that carry out in this database, a lot of the information of the mechanism are entirely incorrect. And on the other hand, there is a Megan data in the under the umbrella of Bilbao crystallographic server. Okay. So this is a very important database on mechanism. It consists of like more than 2,000 magnetic compounds. They are very high quality. All the magnetic information, the magnetic orders, and there are, I believe there are also information about the transition temperatures. They are provided by a real experiment, and the magnetic orders were resolved in terms of X-ray or neutron scattering. Okay. So this is a very important database, but you can easily see that it's limited by the size. So our goal is to find to construct a database with both quality and quantity, okay, on the mechanism. Also, we want to construct this database in a autonomous way that we can comprehensively process a large number of literatures, especially the experimental literatures. Okay. And in the past, there was some effort in that direction. For example, in this work, they used the early version of natural language processing as well as the rule-based text parser to extract chemical information from literatures. Okay. And they also use the same method to collect some of the magnetic properties, for example, the Q temperature. Okay. But since it's rule-based, there are a lot of constraints. Yeah, for example, and it has some reliance on the predefined pattern, and this can recognize if there is a sentence like this, and it knows that the melting point of this compound is 100 Celsius degree. Okay. But if in the paper it is described in that way, and that model doesn't work. And also, if the compound and the corresponding melting temperatures are pretty far away, and there are a lot of sentences in between, and this code will simply pass out. And also cannot understand the very some complicated descriptions in the sentence. So we are seeing the rise of large language models in the past 3 years. And we like to try whether we can use large language model to construct the database. Okay, so our goal is, as I said, we want to autonomous processing of huge number of papers. And our starting point is Elsevier publisher, right? Because they provide API. And there is a journal in Elsevier called Journal of Magnetism of Magnetic Materials. And this is a flagship journal of in the large field of magnetism. And it contains a lot of materials. So we'll choose this journal from which this data will be collected. So our approach starts with the application of the Elsevier API. So this API can it's two-step application. The first step is to use they're the key to search the corresponding papers. Okay? So we want to get the metadata of the papers that is relevant. We want titles, authors, and most importantly, we want the DOI. Then use DOI and the same API, we can download the papers. And we can, but the paper we're downloading is mostly in the XML format. For example, this is the paper, right? And we can use their API to download. But this is what we get. Right? So XMI, yeah, it's a language that is very good for data storage. Right? But there are a lot of self-defined tags, and it's very difficult to process. Okay? So we cannot understand the XML, and the large language model cannot understand either. Okay? So we paid a huge effort in cleaning up the XML and before feeding to the AI models. And then the next is the prompt engineering. So yeah, so this part, yeah, it's very long prompt. Unlike the one that we usually use in the chat box on the web. So it consists of the general mission descriptions, some role player, and here there is also a sentence like this. So because we found that this AI model always confused the ferroelectric material with the ferromagnetic material. So we explicitly asked the AI model not to confuse these ferroelectric materials and the superconducting materials. And yeah, we also educate the AI not to use if there's no information, no corresponding information in the paper, don't make up anything that doesn't exist. Just simply label not available in the database. And this part is the chemical composition. And for chemical composition, the key problem is there are a lot of non-stoichiometric alloys. And in their chemical formula, there is a parameter X. And we asked the AI model to find the value of X in the paper and plug back into the chemical formula. And we also define the output format here. And this is other prompts related to the mechanism. We define the Curie temperature. This is the transition temperature for a ferromagnetic material. And we define the Néel temperature for antiferromagnetic materials. And here we also collect the data of Curie-Weiss temperature that is defined in terms of the magnetic susceptibility. So we explicitly here, I think, yeah. One reason that we collect this Curie-Weiss temperature is the name of Curie-Weiss temperature is so close to the Curie temperature. So sometimes the AI model will confused by these two names. And also here, yeah, we again remind the model not to be confused by ferroelectric materials or piezoelectric materials. And for the magnetic properties, we collect the transition temperatures, coercivity, resonance, magnetic moment, magnetization, stability, and recently we also collect information about the magnet anisotropy, and because this is very, very important in determining the coercivity and the magnetic the energy product of a magnetic materials. So this is the list that we extracted from each paper. And here, yeah, I like to say that the one key achievement here is the lattice parameters. So the paper usually provide the lattice constants and the system, the crystal structures. And this is very important in predicting the magnetic materials, especially if you want to use like GNN, like graph neural network models to make some predictions. And this is our workflow. And this is actually our first version of the workflow. And so start with the papers that we identified using API key, and we use this large language model to check whether the materials reported in this paper is experimental, whether it's experimental result. If it's theoretical result or computational result, we'll simply discard it. Yeah, although I'm a theorist, I have to say that for this magnetic materials, somehow I don't trust much about the DFT results. Okay, so our goal is to collect experimental informations. So then if it's experimental, we keep it. But then at that time, this work was done in between 2023 and 2024. And that time, there's only GPT 3.5, and there was a token limit of 500. But paper, usually the length of paper is much larger than that. So what we have to do is to divide the papers into several pieces. And we use the embedding the RAG techniques to identify the top 5 pieces that are relevant to the magnetic informations that we're interested in. Then we feed this into, again, the larger this GPT 3.5. And then at the end of our work, we found that there was a GPT-4 coming out. Yeah. And the result from GPT 3.5, usually it's a little bit lengthy. Right? And we use GPT-4 to summarize it into this nice JSON format. Okay? And then this will be listed in the database. So this is our first version of database. As I said, yeah, we use this API to process the papers from Journal of Magnetism and Magnetic Materials. And we identified about, we get XML, then we collect them into the database. Okay? So we identified about 20,000 papers containing the experimental characterization of some magnetic materials. And out of them, we successfully extracted like more than 9,000 entries on the magnetic materials. Then you might ask, okay, how can you trust this result?
Question.
Yeah.
Oh, there are 20,000 papers all within Elsevier?
Or they are all JMM.
What?
Journal of Magnetism and Magnetic Materials.
Oh, those are journals in Elsevier.
That's right. That's right.
Ah, I see.
And actually, Elsevier only provide API for papers after 2000. So that time we can only process papers like that.
Uh-huh.
Yeah.
So these are 20,000 since year 2000.
That's right.
Ah, okay.
Yeah, about 20,000 after year 2000. JMM, in JMM, most papers, they are experimental papers. So yeah, so that's why there are.
I see. So that's like a treasure trove. A lot of papers. Oh, okay.
Right. So we use it kind of as a validation of our method. Yeah.
Mm.
Yeah, later I will show that we have some revised workflow.
Mm.
Yeah, but as I said, that time the ChatGPT just came out, and people worry about hallucination. I worry about hallucination as well. And what we did is, you see that this paper has like six students. What I did is to ask these students to spend their entire summer reading these papers and check the results we extracted. So they read like more than 3,000 papers in the entire summer. Yeah, it's a very, very long summer for them. Yeah, but this is what we do at the moment at that time. But later I will say that we have some other smart ways. So after that, we noticed that we missed a lot of data from tables. So here we only process the texts. But about the data in the table, for example, this is a table in the paper, and this is the corresponding XML file. And this is extremely complicated. And we spend a lot of effort using the regular expression, beautiful soup, and other packages. And eventually, we are able to convert these tables into this nice markdown form. And then we can feed it into the database, into the larger model. Also, there are you might wonder, okay, why we spend so much time in processing XML? Okay, what about just feed the PDF to the modern large language models? Then this is the example. The same paper, this paper actually containing the measurement result of 4 materials. And if you feed the XML or the converted XML convert markdown of file into larger model, you can identify all of them. But if you just feed PDF into the model, and it will give you only 2 entries. Right? So there are some information are missing. And actually, there's another more severe problem is there are a lot of papers. They're not in modern PDF format. Right? So they're just scanned images. And for example, this is the early paper. And what we do is we use some code to identify each block. Right? Then feed each block into the larger model and converted this image PDF into a markdown format. Then we feed this markdown format into larger model to collect the information. So yeah, you see that this is one example. There are a lot of even some equations can be nicely converted. Okay. So the reason we are doing all of this is also we found that for old PDF, for example, if there is a data, it's 10 to 5. Right? If we just feed this PDF to the ChatGPT, even the modern one, it will probably tell you it's 105. Right? And this data will be entirely wrong. And sometimes 10 to 5, this superscript 5, is a reference label. Right? So you need to carefully differentiate different labels here, the numbers. Right? And for example, there are sometimes, there are figures in the paper, right? And we can use this code to extract these figures as well. And this gives us the possibility of processing the data in the figure in future efforts. Right? So then use this technique. Right? We can even extract the data from handbooks of some magnetic materials. Yeah, we processed a large number of handbooks. So this is our revised workflow. And we can process handbooks and PDFs, and we also use API. So I would say that we also have agreement with American Physical Society, and they recently have launched their API, and we tested their API, and we can even process all their PDFs. So they give us the access to all their PDFs back to 1900 or 1890-ish. Yeah. So then, we can you can extract information. And here also there is another difference compared to the previous workflow is we at that time there is GPT-4, and the token limit is way larger, and we don't need to divide the papers into pieces. So this you can see that the technique is developing so fast, and it makes the the life easier. But on the other hand, you really need to learn these new techniques and revise the methodology. And hallucination. And yeah, I always like to use this example. Okay? Wherever I give a talk, I will revise this prompt and ask and suggest ask the AI to suggest me a one-day tour. Right? For example, one-day tour in Ithaca. Yeah, it's pretty. Also here you see that I asked the AI not to use any tool call, right? Because usually they will use some tool called Yelp or Google Map, I don't know, okay, and they give you a better answer. But I explicitly asked it not to use it and just to see whether the text processing would give us the decent answers. Okay. I think most of them are real. I checked the Google Map, and there are very beautiful state parks around. But they always have some problems in suggesting restaurants, which I care the most usually. Okay. So, for example, there's Moosewood in the neighborhood, right? Uh, and there is a very nice Ethiopian restaurant. I also found it, but I don't think this is real. Uh,
It used to be, I think we
it
used to
used to
have,
be.
yeah, I think we had, I think so.
Oh, I see.
Yeah.
So
I don't know,
it's doing
maybe.
much better. Yeah, like I give one talk last year, exactly 1 year ago, and all the restaurant they provided are not real. Yeah. So
Yeah,
you can, yeah.
It's
I just checked.
closed. We used
It's
to have it.
permanently closed.
Yeah.
I've
I
eaten
see.
there.
Yeah, because I
It
checked it
was
and I
real.
found the nearest restaurant with this name is in Colorado.
Yeah, so we used to have the restaurant. It
I
might
see.
be the
I see.
one that got the truck running into it or
Yeah.
something.
Yeah. So
Yeah.
somehow the hallucination is getting better and better controlled in the modern language models. And also here, what we did is we randomly select about 5,000 records in this new database, and we use other language models, okay, like Gemini 2.5, to validate and have the cross check. And again, I did the same check as the student to read randomly 500 papers just for manual review. Okay. And this is the performance. And you can see that the accuracy is pretty good. And overall, all these information collected have the accuracy about 95%. But
I have a question. How is Gemini and the data from the student, like, was that reflected in this data here? Is this all Gemini, or it's the
so
parentheses?
this is Gemini. This is Gemini, and the number in the parentheses are students.
Got it. I
Manual
see.
review. Yeah, yeah.
Okay.
So this column shows that the data is successfully extracted, cross validated, and this column is also good. Just shows that this data is not contained in that particular paper, and this is true, validated by other models or by the students. Yeah, these two columns are not very good. Yeah, but overall, you see that the accuracy is it's pretty good. Okay? Yeah. So I will say that any database contains mistakes. Okay? And especially here, we are using this database to predict materials using machine learning models. And the machine learning models have their own accuracy. Okay? And as long as the accuracy here doesn't affect the performance of larger models, I will say that this is good enough. Yeah, so But there are something that we also need to improve a little bit, like lattice structures here, okay? Because the description of lattice structure is very complicated. Right? So sometimes the paper use the point group, sometimes use the space group, and sometimes use the number of the space group. Yeah, or sometimes just simply say the crystal system. Yeah, so this is why it's very complicated. But I think this problem can be easily overcome by connecting this data to other DFT database. For example, a materials project or ICSD, because they have much better structure informations. And this is the database. The statistics of the database, the current temperatures, the new temperature distributions. To my surprise, 65% of the material we collected are ferromagnetic materials. Because previously I thought the antiferromagnetic materials is very easy to design. And in principle, any transition metal oxide, yeah, you can fine-tune the number of valence electrons and to use the superexchange mechanism to make it antiferromagnetic. Right? But it appears we have more ferromagnetic. The reason is ferromagnets, we contain a large number of alloys. Right? And for example, iron alloying to other elements. And we can make infinite numbers of ferromagnets in this way. So that's why there is a large number here. And this is the distributions of the other key magnetic properties, magnetization, coercivity, and anisotropy. Yeah, we collect anisotropy in this work as well, resonance. And the most important thing is the magnet energy product. And we list all this data in the this Northeast materials database. Altogether we collected more than 60,000 entries, and I would say that some entries are talking about the same magnetic materials, because the one magnetic materials might be reported by different papers, okay? But we just collect them all. And in the following materials predictions, and we will clean them up by taking the average values from all these papers reporting the same material. And yeah, so there is a button here called the random magnetic material, and you can click it, and it will randomly give you a magnetic material and its information. Yeah, so this is the one click, and if you click again, you'll probably get another one. And here you can explore and search the compounds that you're interested in terms of the elements involved. And for example, we want the materials with iron, cobalt, and nickel. And there are some eight compounds reported. And recently, we also create a portal for the community to contribute their published or unpublished data. And we hope that this is the database that will continue to expand. And you might also notice that in this website, we also published two other databases constructed using exactly the same method. Okay, one is the thermoelectric materials, and the key quantity is the figure of merit defined in terms of this Seebeck coefficient, electric conductivities, and thermal conductivity. And we collect all this information as well. And for the audience, probably you're more interested in the superconductors. Right? And this, we collected like 78 superconductors in this database. And this is the count, okay, as a function of the transition temperature. And there is a peak here, and this peak is the cuprate peak. And there's a peak here. I don't know whether it probably it has no correlation with the peak of nictates. And yeah, we collect the transition temperatures, structure as for sure, and the critical fields. But I think is it including here? maybe it's not, yeah, here, right? We also collect their pressure, right? Because this pressure is a very important quantity as well. I don't think a lot of, some of this data can be, especially like, for example, the pressure can be computed in terms of DFT. So based on this,
Jiadong,
yeah,
but it's the critical fields are not always reported, right?
right. So if
Mhm.
yeah, it depends on the type of the superconductors. Yeah,
Uh-huh. So I guess sometimes you'll have to combine multiple sources to
that's
collect
right.
all the information
Exactly,
for a given
exactly. But
material.
for each entry, we just collect the paper, one paper, the information from one paper.
I
For
see.
example, this paper, yeah, present all this, and so we collected. But another paper may only have the chemical formula and the transition temperature, and the others are not
And that
available.
becomes a different entry. Each paper is an entry.
Exactly, right.
Uh-huh.
It will be a different entry.
So
Yeah,
this is kind of a thumbnail version of the paper.
that's right. That's
Mhm.
right. Yeah. So we're not saying that we collected, yeah, maybe this is confusing. We are not collecting 78,000 superconductors.
You have
Different
78,000 papers.
entries, yes. Yeah.
Mhm.
At least containing the information of the transition temperature of the critical temperature of the superconductor.
Mhm.
Yeah.
And for the thermoelectric materials, how did you decide which properties to collect? Like you have to decide what you're going to extract, right?
To describe what?
How did you decide which property to extract?
Yeah, so you need to revise the prompt.
Uh-huh. So
Yeah.
you decided what to extract yourself?
So yeah, so if you're getting to a new field, right? So you need to know what is the important quantities.
Right.
So yeah, so we first studied the thermoelectric material papers and noted identify these key quantities. Then we revise the prompt. So in the future, we also want to have some like autonomous generation of the prompt for any field, so that then we can use this method to build database, yeah, of any field. Yeah, but here we just do it one by one. Like for superconductors, yeah, we will revise the prompt accordingly. Yeah. Then use this database, we try to predict, and we try to train models. So actually, we are not expert in the training models and make the predictions. But the point is, we don't know how to publish a paper just on database. So yeah, we have to somehow use this database to generate some science. Right? So that's what we try. And so yeah, we made models, very simple random forest models for the classification, okay, given a new material, whether it's ferromagnetic, antiferromagnetic, or non-magnetic. Then if it's ferromagnetic, then we will use the regression model to predict its cure temperature. And hopefully, and it will be experimental validated in the future. So we use this method to screen the materials from the materials project. So this is the result. Yeah, we use this random forest model for the classification. And this is the confusion matrix. All the quantities in the diagonal are what we want. And using this method, we identified some materials in the materials project. Okay, this list materials. They're listed, for example, this one is listed as ferromagnet, but our model predict it's antiferromagnet. And this list of models and materials actually were experimentally synthesized and characterized, and they're consistent with our prediction. So this also confirms that there are a large number of labels in the materials project are not correct, especially for the purpose of magnetism. And then we can predict the Q temperature. Use random forest, another variant of the random forest, this gradient boosting, and we use ensemble neural networks. And the R2 value are decently good, and based on this, we predicted a list of ferromagnet materials from the materials project. Again, we find some materials that were actually experimentally synthesized. And here we only list the materials with the predicted Q temperature above 500K. Right? So they're in general, the trend is consistent with the predictions from various models. And we also identified some new antiferromagnets with large new temperatures. So I will skip that. But we also like to see whether
among your predictions, were there rare earth-free magnets?
there are some of them still have this.
I mean,
a lot of them are rare earth free. Yes, so this is because
it's free.
It's materials project.
I see.
But even rare earth free, right? Some materials, if they use platinum or some like rhodium, and we will say that these are not interesting materials.
Too expensive.
That's right. But at this point, in that paper, we only predicted the Q temperatures. Towards the end of the talk, I will show you some recent results that are not published yet. But it gives the predictions of the magnetic energy product, and this will be more exciting. So we use we try to see whether this fine-tuning larger models can have some prediction powers. Because there is a transformer, the attention mechanism built in there. Apparently, this figure is generated by AI, Nano Banana. Because by fine-tuning, you can provide some domain-specific knowledge into this general larger model. And actually, what it does is on top of these parameters from the pre-trained larger model, and we'll include some parameters, some low-rank parameters, and we use the domain knowledge to revise to train this small number of parameters, and so that it can give some better performance for this discipline. And this is how the model is fine-tuned, and we give the instructions again, role players, and what to do, and what is the what the output, and the input is all the information that we have from the database that we constructed, and the chemical formula. Chemical formula, the structures, and the magnetic informations as well. And we want output some Q temperatures, coercivity, and isotropy, all this information that we're interested in. So this is the workflow, and we use this supervised fine-tuning, and then we use the data from our database to make some attempts of reinforced learning. And we do see that this reinforced learning significantly improve the performance of the model. So this is the classification in terms of supervised fine-tuning, small open source models, larger models. And then, this is the key result. And this is the supervised fine-tuning result on the Curie temperature prediction, saturation magnetization, and magnetic crystalline anisotropy constant. Okay. You can see that there is some data here. They're in the horizontal dots, and they're basically saying that the model is making wild guess. There's no judgment of these compounds. But after the reinforced learning, and in terms of the data, by feeding to the values we collected in the database, and you can see that the R2 performance has been increased significantly. So this R2 is still not as good as the traditional machine learning models. But this because one reason is the GPU we used to train this model was in a workstation that I purchased 10 years ago when I started my professorship at this university. So it's very limited. But this just show a trend that this supervised, the reinforced learning and larger model can indeed do some acquire some prediction power once there's more data that chain and more epochs are processed. And this is the key magnetic energy product. And this is our predictions of the new materials. And some materials we are really very interested in and want to use DFT to validate. For example, this aluminum, iron, hydrogen. It is rare earth free. And the aluminum, iron, hydrogen, they are all very cheap. And the magnetic energy product is pretty high for some reason. We would like to use some physics input in terms of DFT to understand these materials and also to validate our model. And we use the same method to predict superconductors as well. So these are the material ID in the genome. But somehow a lot of them are hydride. So this is not very good because the hydride superconductors, they probably are BCS. And some DFT calculations can also reveal some of the physics. But we like to see whether this can be applied to other models and make more predictions. So I'll conclude my talk by some discussions. So first of all, I like to say that this workflow for the database construction is very general. And we really like to apply this method to collect some properties that cannot be easily computed by DFT. For example, the strongly correlated or any physics at finite temperatures. Probably it's not easy in terms of DFT. Also, there are some materials, some properties will be sample dependent. For example, the coercivity field that I mentioned. Coercivity field and the magnetic anisotropy, they're closely related. But coercivity, magnetic anisotropy give a kind of a upper limit of the coercivity a material can have. In order to increase the coercivity, one need to have some microstructure processing in the material synthesis part. And so there are also other interesting databases that we like to construct. For example, the structure transitions and the synthesis. Because a lot of materials we predict, any machine learning model predict, they're probably a metastable state. And how can one experimentally synthesize these metastable compounds? So this need some idea of the synthesis, the precursors, the synthesis conditions, and by collecting this data, and probably can have a it's kind of we try to collect all the experience from the experiments. And we, as I said, we like to use the multimodal models to extract the data from figures, and this can significantly enlarge the size of the database. And we also build a MCP and for the AI applications of our models of our database, and we like to have some autonomous prompt generations. And actually, it inspires some. As I would say that the AI will inspire new publication mode. For example, what we did shows that the objective data is more important than the subjective descriptions. Right? So maybe in the future, how a material is reported in papers will be different as what we are doing right now. Okay. So the final comment is, so this work was done by these two excellent students. And so condensed matter, especially condensed matter, I will say that it's a field that in the past was dominated by senior people, okay? Because you really need to build experience in order to understand some new phenomena. But with the rise of AI, I'm seeing a trend that this new generation are literally leading all these efforts. Okay? So a lot of the technical details that I presented today, I totally don't know, and it totally relies on these two students. Yeah. Okay. So with this, I'd like to thank you for your attention.
Thank you so much. So right now we are going to turn off the streaming to YouTube, and we're going to move to Amy internal discussion.